So what we're going to look at here is section 8.7. It's the variation of parameters. And so this is another way of solving for that particular solution when we already know the solutions to the homogeneous differential equation. What we're primarily going to look at here inside of this lecture is we're going to look at it for second order differential equations. There's another method for higher order differential equations that we can also use that is very similar to this one, and we can address it in a later lecture. Okay, so this is the first part. This is the general variation of parameters. Then we'll do something called Green's function in another lecture, and then maybe in another lecture we'll look at the generalized variation of parameters for more than second order differential equations. Okay, so we use the variation of parameters. Okay, so this is used when we cannot use the method of annihilators. All right, so it's way more way more facile. It's not necessarily easier, okay, but what it is it is definitely something that we can use in a lot of different situations, and it almost doesn't matter what f of x is for us to be able to use this method, okay? So if we can't use the method of annihilators, we don't have the right form to use the method of annihilators, we're going to use variation of parameters, okay? So let's suppose you have a dE. Y double prime plus a1 y prime plus a2 y equal to f. Okay, so it's not homogeneous. We have an f of x, and in this case, we're not going to be able to use the method of annihilators. Okay, and suppose that we know the solution to y double prime plus a1 y prime plus a2 y equal to 0. So that is that we actually know the solution to the homogeneous differential equation, and it doesn't necessarily have to be one that has constant coefficients. From our perspective, we're going to use ones that have constant coefficients, but in some cases you might not have constant coefficients, and so you can still use the variation of parameters even if you don't have those constant coefficients. Okay? All right. The method we will use will replace C1 and C2 in the homogeneous solution with two unknown functions, u1 and u2. Okay, u1 and u2. All right. Such that yp, right, our particular solution is going to equal u1 of x, y1 of x, plus u2 of x, y2 of x. All right. Since we've already been given solutions to both y1 and y2 when we solve the homogeneous part, right? Okay, so these are the solutions to the homogeneous part. Our job is to find u1 and u2. And how we're going to do that is with this method of variation of parameters. So we want to solve for, okay, yp equal to u1 y1 plus u2 y2. Okay, and what we're going to need is we're going to need a constraint. Okay, and this constraint is going to be actually very important, but it will then allow us to do a lot of solution, and that's going to be that u1 prime y1 plus u2 prime y2 will equal to 0. All right, this is our constraint. okay? And once we have that constraint, we're going to utilize this information. We will use this to then solve for yp double prime plus a1 yp prime plus a2 yp equal to f. Okay, so basically what we're going to do is we're then going to use that in order to solve this. All right, what it'll do is it'll actually set up a system of equations that we're then going to utilize Kramer's rule in order to solve. Okay, so that's why I gave you the pre-lesson on Kramer's rule, just to remind you how it is that you do it. Okay, so that when you see it here, you have less of a problem figuring it out. Okay, all right, so let's start. Okay, we begin with this hypothesized, we begin with the solution, okay, of yp equals u1 y1 plus u2 y2, okay, along with our restriction, okay. So what we'll do is we'll figure out, okay, so, and by the way, we should state our restriction, u1 prime y1 plus u2 prime y2 equals 0. All right, great. Okay. Now, that we're going to then find yp prime. Okay, so yp prime is then going to equal u1 prime y1 plus u2 prime y2 plus u1 y1 prime plus u2 y2 prime. Okay, now what we want to notice is that this whole thing right here, that equals 0, right, by our constraint. So yp prime is going to end up equaling just u1 y1 prime plus u2 y2 prime. Okay, and then we're going to have yp double prime is going to equal u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. Then what we're going to do is we're going to substitute in back into yp. Okay, I'm going to do that on the next page. So yp prime, or excuse me, yp double prime plus a1 yp prime plus a2 yp will then equal our f of x. Okay. All right. So now what we're going to do is we're going to input in yp double prime. Okay. So yp double prime was u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 u2 y double prime. Then plus what we're going to get is we're going to get u1 y1 prime plus u2 y2 prime times a1, and that's going to be our second term, plus, and then finally we'll have the original function u1 y1 plus u2 y2 a2, and that's our third term. Okay, now what I'm going to do, and that's going to equal f of x. Now what I'm going to do is I'm going to first take out this u1 prime y1 prime plus u2 prime y2 prime. Okay, and now I'm going to group together all of my u1 terms, okay, and all of my u2 terms. Okay, not that one, excuse me, just the u1 and the u2 terms. Okay, and so what I'm going to get is I'm going to get, okay, u1 times y1 double prime plus a1 y1 prime plus a2 y1 plus u2 y2 double prime plus a1 y2 double prime plus, excuse me, yeah, a2 y2, and that all equals f. Now here's the thing, because y1 and y2 are solutions to Ly equals 0, right, the homogeneous part, this means that these two, that one there, okay, Ly1 equals 0 and Ly2 equals 0, okay? Y1 and Y2 are solutions to the homogeneous part, so those two terms, they have to equal 0, right? Take a look, that's your differential equation. So what we end up with is u1 prime y1 prime plus u2 prime y2 prime equals f of x. And that's what we end up with. What we're going to do is we're going to use that function and the constraint, right, to construct a system of equations for u1 prime and u2 prime. Okay? And so let's take a look at that. So what we have now is we have first that we had u1 prime y1 plus u2 prime y2 equals 0. That was our constraint. And u1 prime y1 prime plus u2 prime y2 prime equals f of x. So what you want to see here is that this is now a system of equations. This is equivalent to, okay, y1, y2, y1 prime, y2 prime times u1 prime, u2 prime equals 0 and f of x. So if we solve that system of equations, that's going to give us u1 prime and u2 prime, which is what, well, it's not what we're looking for, but it's going to get us really close. Because then all we've got to do is we've just got to take the integral. We take the integral of u1 prime, we take the integral of u2 prime, and what we end up with is ta-da, u1 and u2, which are what are necessary for us to, in fact, solve the differential equation, to get yp. Okay? All right? So how do we do that, right? We will use Kramer's rule. We will use Kramer's rule to solve for for u1 prime and u2 prime. Then we will integrate to find u1 and u2. Using Kramer's rule. We have our A. A is equal to y1, y1 prime, y2, y2 prime. Excuse me. And our B, okay, is going to equal 0 f of x. All right. One thing to notice here is that A is the matrix for the Wronskian. So I'm going to use that. I'm going to actually matrix for the Wronskian. Okay. So I'm going to use that fact, and I'm going to be writing it as, when I find its determinant, I'm going to call it the Wronskian, because it's the Wronskian for y1, y2. Okay. So according to Kramer's rule, right, our first u1 prime, okay, is going to equal, what we're going to do is we're going to take the determinant, and we're going to take the determinant of the matrix where we replace 0 f of x with the first column, and then y2 prime with the second column. So that remains the same. And then we're going to divide by the determinant of A. Well, the determinant of A is the Wronskian for y1, y2. Okay? Then u2 prime is going to equal, right? We're going to take y1, y2 prime, or excuse me, y1, y1 prime, and then 0, f of x is the second column, and we're going to divide that through by the Wronskian of y1 and y2. And that's going to give me u1 prime and u2 prime. And then it's just a matter of multiplying. All right, so this one here, it's going to end up equaling negative y2 f of x over the Wronskian of y1, y2. And u2 prime is going to equal, okay, y1 f of x divided by the Wronskian of y1, y2. And there's your functions. That's actually u1 and u2 every single time. So we're going to use that fact, okay? In fact, we're going to use that fact in order to make everything a lot easier. I'm going to do an example, but you can probably, after a little while, see, we don't necessarily have to go through the whole setup. We can actually just utilize these equations. In fact, that's what I'm going to do, okay? All right. Now, u1, right, prime, if you remember, okay, is going to equal, we said, well, you just wrote it, so of course you remember it. It's only been a second for me. It's going to equal negative y2 f of x over the Wronskian of y1, y2. And u2 prime, okay, is going to equal y1 f of x times the Wronskian, or divided by the Wronskian of y1, y2. Okay? So we'll take the integral of both sides, right, with respect to dx, and that's going to give me u1. And this one here is going to give me u2. There it is. Okay? So yp is going to equal y1, remember, because we've got to multiply by y1. Okay? y1 times the integral of y1, y2, this is negative. Okay, so it'll be negative y1, y2 f of x, Wronskian of y1, y2, plus y2 times the integral of y1 f of x, Wronskian of y1, y2. And that's your particular solution. Kind of theoretical. We'll get into it a lot more. I'm going to actually give you an example so that it kind of, gels together. And hopefully it makes a lot more sense when we take a look at that. Okay? All right. Let's go on to that example. So let's take an example. All right, and that's going to be y double prime plus y equals tan x. Okay? All right, so the first thing that I need to do is I need to solve Ly equals 0. Okay? Well, this differential equation is going to be d squared plus d squared plus 1 y equals 0. Okay? And so my solution will be yc equals c1 cosine x plus c2 sine x, right? Because we have a complex root to r squared plus 1, so consequently we're going to have a complex solution to Ly equals 0. All right, so that means that y1 is going to equal cosine x, and y2 equals sine x. Okay, cool. So that's great, right? Then all I'm going to do is I'm actually going to go in and I'm going to utilize Kramer's in order to solve this differential equation. Okay, so I'm going to set up A. A equals, all right, it's going to be cosine x, and then negative sine x, and then sine x, and cosine x, right? And we're going to multiply that by u1 prime, u2 prime, okay? And that'll equal 0 f of x. Excuse me, not 0 f of x, but 0 tan x, because we know what f of x is. F of x is tan x. Okay? So u1 prime, okay, is going to equal 0 tan x sine x cosine x divided by the Wronskian of cosine x sine x. And u2 prime will equal 0 excuse me, not 0, but cosine x, negative sine x, 0 tan x, divided by, again, the Wronskian of cosine x and sine x. So what I need to do is I need to find the Wronskian. The Wronskian of cosine x sine x equals, and that's going to be the derivative, or the, excuse me, the determinant of cosine x, negative sine x, and sine x cosine x. And that'll end up equaling cosine squared x plus sine squared x. Okay, which equals 1. Great. How tidy. Okay, so then we know that u1 prime is just simply going to equal, because we're going to divide it through by 1, is going to equal 0 tan x sine x cosine x, which is just going to equal negative sine x tan x. And u2 prime is going to equal cosine x negative sine x and 0 tan x divided again by 1, and that'll equal then cosine x tan x, which simply equals sine x. All right? Now, u1 is going to equal the integral of negative sine x tan x dx, and u2 will equal the integral of sine x dx. Okay? The integral of the negative sine x tan x equals, you can go in and you can check this for yourself, negative natural log of tan x plus secant x plus sine x. And the integral of sine x is negative cosine x. Now we need to multiply by y1 and y2 to get yp. Okay, so yp is going to equal, well, y1 was cosine x, so we're going to take cosine x times negative natural log of tan x plus secant x plus sine x plus, okay, sine x times negative cosine x. And this will thus equal, well, the cosine x and the sine x and the sine x and the cosine x will end up canceling each other out. So this will end up giving me cosine x, or the negative cosine x ln of the absolute value of tan x plus secant x. Okay, and so y is going to equal c1 cosine x plus c2 sine x minus cosine x ln of the absolute value of tan x plus secant x. Okay, so this is going to take some time, right? You're going to have to actually spend some time working through some of the problems, working through like my examples. We'll do some work like this in class. But in the end, it's basically, you know, just some work that we've already done with linear algebra, Kramer's rule, right? Solving a system of, in this case, differential equations. And then after that, going in and using some integration, right? Just like any other differential equations. We're going to end up doing some differential equations, okay? So take a look at this. What we're going to go on to next is we're going to talk about Green's function.